We all know the story. Thomas Edison went into his lab, tinkered with glass and wire, and walked out with the working light bulb. The only problem is, he didn't. By the time Edison filed his patent in 1880, inventors had been demonstrating glowing filaments for 40 years. An Englishman named Joseph Swan had even patented a working carbon filament lamp before Edison's was finished. If the core engineering problem of the 19th century was simply making a piece of glass glow, in the dark, Edison would be remembered as a minor footnote in history. The real challenge was taking that parlor trick and scaling it, figuring out how to power a densely packed city from one central generating plant. And standing in the way of that centralized grid was a brutal economic constraint. Sending electricity over distances requires heavy copper wire to carry the current. The actual design problem facing early lighting pioneers was building a distribution network that wouldn't immediately bankrupt them by consuming thousands of tons of expensive copper. This is where Edison made a deeply counterintuitive decision at the concept stage. Inside his bulb, he actively chose to use a paper-thin, highly resistant filament. A high-resistance filament physically struggles to pass energy, making it harder to glow. But as resistance increases, the required electrical current drops sharply. Lowering current shrinks the copper cable diameter, allowing the grid to use affordable metal instead of impossibly thick lines. The specifications of Edison's glowing filament were dictated entirely by the economics of the supply chain. He was making a macroeconomic systems decision, wearing the costume of a bulb design. With the high-resistance constraint locked in, Edison's team had to design backward to build the ecosystem that would feed it. They engineered entirely new infrastructure, eventually leading to these 27-ton coal-fired dynamos installed at Pearl Street Station in Lower Manhattan. The grid required secondary inventions, constant voltage dynamos for even power, and parallel circuits to prevent blackouts. But the final, most crucial component of this architecture had nothing to do with generating light. It was the device that allowed the electrical energy to be monetized. An unbillable invention is a hobby, not a business. The glowing artifact at the end of the wire represented maybe a tenth of the actual innovative labor required to make the whole enterprise survive. That dynamic remains a universal law of product development today. The visible artifact that consumers purchase is almost never the actual design. Take a modern electric vehicle. Drivers pay for the sleek lines of the car itself, but the vehicle is effectively just a visible node attached to a massive underlying global charging network. Or consider your smartphone. The glass rectangle in your pocket is essentially a portable delivery mechanism for global app distribution and digital payment processing. There is a strict competitive trap here. Brilliant innovators who focus strictly on perfecting a single, isolated object will consistently lose the market to slightly compromised objects that are purpose-built to integrate into a larger system. The invisible infrastructure operating beneath the surface quietly dictates which products survive and which become historical footnotes. When an initial concept is exciting, the temptation is always to polish the visible object and defer the unglamorous system it relies upon to function. Don't fall into that trap. At Depix, we treat this as close to a law. Design decisions are cheap as a sketch, brutal once tooled. See every angle before you build.